Hi guys, this is our last video on chapter 7 and it's basically going through the last bit on the binomial distribution. Now with this video we're going to be looking at the concept of making a binomial distribution normally distributed, and the reason why we do that is because if you think about when we do the binomial distribution and using the CDF, it only ever works from left to right. Okay, so and if you obviously got two values, then you have to do two calculations. So if you have an upper limit and a lower limit, then you have to do two calculations, and it's a bit messy. So it's much easier for us if we consider a binomial distribution being normally distributed, and then we can just do that. But there is a bit of playing around with that I need to show you as well. The first thing is we just review some of the technology that would be, or the terminology that we've been talking about. All right, so we understand what bin NP means. So that is the number of values that we have in our distribution, and then the likelihood of a successful event. Then if we do a distribution now, the general rule is if a distribution is, if the n value is greater than 30, doesn't matter really what it is, most of these distributions will become what we call normally distributed. So you can see here's an example of a bigger sample. All right. Now the rule is, and if you can prove this, then you're able to use the normal distribution for a binomial. Alright, so the rule is you must show that n is greater than 30. Alright, when you do n times by p, then that has to be greater than or equal to 5. N times by q has to be greater than 5. Now, when that's the case, we have our mean value over here. Our mean value is equal to n times by p, and our standard deviation is going to be the square root of npq. So once we've got that, we can use this information to find our mean and our standard deviation. Then we can use our normal distribution. Alright, so that is really important. Now, there's one other finer detail that we need to be considering, and we'll go through this with our example. But if you look at the close-up of this diagram over here, let's say we're wanting to look at something where it's either greater than or less than 10. So this is our value. Right, so that's 10 on our scale here. Now, because we have an either right or wrong answer, so 10, and we put it into a histogram, right? So if we're looking at the upper side of 10, then we would be looking at, and this diagram, by the way, is back to front. So when we're looking at that, on this side, we've got 11, okay? So 11 corresponds to a line being right in the middle there, where our distribution is. Right, and 10 is a line right there in the middle of our distribution. Alright, so if you allow for the width of that box, and this is what we call the correction coefficient here, right, this side over here is going to be 10.5, and on this side over here it's going to be 9.5. Right, so if I'm looking for a value, say, greater than 10, then I need to be considering this value, 9.5. If I'm looking for a value less than 10, then I have to be considering that value there, 10.5. All right, and we'll make that clearer when we start doing a couple of examples. All right, so I think probably the easiest way to understand this is actually to do it. All right, so let's just go through this example here. So we're tossing a coin 500 times. What is the probability that falls between? So when if I was doing between there, that's tricky because I'll have to look at below 240 and then below 260 and take those two results away. So it'll be easy if I can show that's a normal distribution. So clearly n equals 500, and so that's greater than or equal to 30. So that's ticked. Okay, we're happy with that. That's fitting the rule. N times by p, so that's going to be 500 times by, now a coin is a 50-50 chance, so that's equal to 250, so that's greater than or equal to 5, so that's true. And then n times by q, now q is obviously still a half as well, so that's going to be 250, so that's greater than or equal to 5, so that's also true. So we've satisfied all of these conditions, so therefore this bin 500 and a half can be said to be normally distributed. Because we've shown those information there. All right. So the other thing that we need to work out is we need to work out our mean value. Now, our mean value is simply n times by p, which is in fact 250. All right. So I don't need to redo that again. And I also have to work out my standard deviation. So that's going to be the square root of 500 times by half times by half. Now do that in a calculator just to do that. So that's the square root of 500 times by 0.5 times 0.5, and that gives me an answer of 11.18. Alright, so that will be good enough for that. So that's equal to, approximately equal to, so 11.18. Alright, so now I've proven this is normally distributed, I can now use my normal distribution. Alright, so but I have to also keep in effect the correction that I need to make as well. So what's the probability that it falls heads on 250 occasions? Alright, so probability that x equals 250, then what I'm looking for there is I'm going to, well, for this one here, I mean, it's probably just as easy to do your binomial because it's a one-off result. So for this one here, I could actually, if I wanted to, do my binomial PDF. Right, it's probably easier to do it that way. So that's 500, a half, and we're looking at 250. So I go to my calculator, and then I can go binomial, PDF, come down. So that's 500 trials. 0.5 is my likelihood of getting a win or a loss, and I'm looking for 250. And that tells me that I've got a 3.57% chance, haven't I? Alright, so that's going to be equal to, approximately equal to 3.57. So it's a 3.57% chance. Okay, that I'm going to get 250 heads when I'm actually rolling that. Alright, so more than 255. Okay, so 255, so B, so probably that X is actually greater than or equal to 255. Now, what we have to consider here is if we were looking at our thing here, right, so 255 would be this line here, 255. We need to consider all these things greater than that side there. Because I've got the width of my box here, the critical value that I'm looking at there is going to be 254 and a half. I've got to allow for the width of that box. Alright, so what we say here is that's going to be the probability of X, and we put a little star on it just to indicate it's a corrected. So it's greater than or equal to 254.5. Alright, so now we can use our normal distribution. So normal CDF, and our lower value is going to be 254.5. Our upper value is e to the 99. Our mean value is 250. Our standard deviation is 11.18. So now I go to my calculator and I use that as my example. Alright, so we go into our calculator. It's probably easy because it's actually easy to get to on the calculator as well. So my lower value is 254.5. My upper value is in fact going to be e to the 99. Remember, we don't have it, we make it that value. Our mean value is 250. Standard deviation is 11.18. And and then we paste that in there, and that will tell us our value. So it's actually 34.37% chance. So that's approximately equal to 0.34. God, I've got a bad memory. Sorry, 37. All right, so 3437. So 34.37% chance of having more than 355. So the important thing there is that correction coefficient that we need to do there. Now this is where it becomes really useful. How about what's the chances that we get between 240 and 260? Right, between 240 and 260. Now the question you've got to ask yourself is, we can include 240. Okay, because it's actually between 240 and 260. Alright, so the correction coefficient that we need to be considering is between those two values. So the probability that x is greater than or equal to 240 or less than or equal to 260. Alright, so my correction coefficient is going to be this. Okay, on the smaller side, it's going to be 239.5. Alright, that's my x corrected. Alright, and then on the other side, it's going to be 260.5. Alright, so I'm allowing for the width of that box. Okay, so then that becomes my normal CDF. My lower value is 239.5. My upper value is 260.5. My mean value is 250, and 11.18 is my standard deviation. So I'll go back to my calculator. Alright, distribution number 2. Alright, so that's going to be 239.5. My upper value is 260.5. Right, 250, that all stays the same. So then it's just a matter of putting it in there and working it out. So I've got a 65.24% chance. So approximately equal to 0.6524. Okay, so I've got a 65.24% chance of, in fact, getting between 240 and 260 heads. So that's the sort of question that you would want to basically have an example of. Now, if we go back to a multiple choice question one, let's say we had a test which has got 50 multiple choice questions. Okay, so if I did my bin 50, and then I did the chances, and if I had 5 options, then the chance of you guessing randomly would be 1/5, wouldn't it? Alright, so in this particular case, what would we say? N is greater than or equal to 30, tick. NP, so if I did N times by P, that will be equal to 50 times by 5th, which will give me 10. And that's greater than or equal to 5, tick. And then we could do NQ, now that's going to be 50 times by 4/5, that's going to give me 40, which is greater than 5, so tick. Alright, I could work out what my mean value is. My mean value would be, in fact, 10. My standard deviation would be 50 times by 1/5 times by 4/5. So do it on the calculator. Square root of 50 times by 1/5, so that's 0.2, times by 4/5, which is 0.8. That's going to give me 2.83. Right, so my standard deviation there would be 2.83. Now I could ask questions like, what would be the chances of you, probability that X is, a person scores greater than or equal to, say, 20 questions correct. Okay, so if that's what I was doing, then remember my correction coefficient then I'd be looking at my probability that my x is star is greater than, if I'm looking at greater than or equal to, so that's going to be greater than or equal to, and I'll have to go the lower value, 19.5. Alright? And then if I was looking for the probability that x is greater than, say, 25 and less than 30, then what I'd be saying over here is the probability that my x star. Now, if I was basically looking at that, I'd be saying that's going to be greater than or equal to 26 and less than or equal to 29, wouldn't I? So then that would become equal to lower value would be 25.5, and then my x star would be less than or equal to 29.5. So you get the idea that the lower value you go lower by a half, the upper value you go greater than by a half. Alright, so let's look at the example and we'll do this properly. Probably that x is greater than or equal to 25. Okay, because that would maybe be a pass mark, wouldn't it? So then we'd say the correction coefficient of x star would, because it's greater than, so we have to say it's greater than or equal to 24.5. Okay, so we've already worked out our values over here, so what we're saying is this would be not a binomial, it's a normal. Okay, so the idea of making this really easy is going to be the normal distribution, so normal, and it's CDF. We're saying our lower value is 24.5, our upper value is going to be e to the 99. Our standard deviation for that worked out to be 10. Our mean was 10 and our standard deviation was 2.83. So then I'd go to my calculator, second function distribution number 2. Alright, so then we're looking at 24.5. We're looking at upper value is e to the 99. We're then looking at our mean being 10, our standard deviation being 2.83. Alright, and we paste it in there. We get a 1.5 by 10 to the minus 7. Alright, so that's approximately equal to 1.5 by 10 to the minus 7. Remember that value is very slim, so chances are I would say it's approximately 0. Right? You've got 0% chance, or you really got 1 in a million chance of actually getting a pass mark by just guessing for that question. Right? If I had one more question there, probability that x is, if I said x is less than or equal to, get my symbols right, if my x is less than or equal to, probably better if I actually write the x value first, makes more sense then. The probability of my x being less than or equal to 10, then that's equal to the probability that x is less than or equal to, now because it's a upper value we have to go above it, 10.5. We don't designate that as being corrected there. So when I do my normal CDF, then that's going to be my lower value is minus e to the 99. My upper value is 10.5, 10 and 2.83. So we're just treating it now like just a normal distribution question, which are really easy to do. So therefore we're going to our distribution number 2. Our lower value is minus e, make sure you use that minus by the way, e to the 99. Our upper value is 10.5, and then everything else is the same. We just paste that in there and away we go, 57.01% chance. Alright, so when we go to, now keeping in mind, when we start looking what that value is, so that's approximately equal to 0.5701, 57.01%. So the chance of you scoring less than 10, you've got about a 57% chance of scoring less than 10 by just guessing through a multiple choice question test, out of 50 marks. All right, so high percentage that if you don't know the answers, you're going to get a fairly poor score. All right, so, and we've shown up here before, if you want to pass it, just by guessing, you've got no chance. Okay, very, very rare would someone be able to do that. I mean, it could happen, all right, but it's not likely to happen. Now, that really finishes this chapter. We will be going obviously on to looking at doing a test just on this chapter, looking at the normal distribution and the binomial distributions, and I'll talk to you in class about what you need to know for that. So good luck with those questions. It's the same as what we're doing. Now, in any of these situations, if you've got a binomial situation which you can prove is normally distributed, it is much, much easier to use your normal distribution. All right, so I suggest that you do that, but you don't have to. I mean, you can do it the other way, and both methods are correct. So good luck with those questions, and I'll talk to you in class if you need some help with that.